Hello everybody, this is Mr. Parham. We're going to be talking about another lesson today. We're going to be talking about nuclear radiation. So we're still in Module 1, still talking about the atom, but this time we're going to go and talk about like the nucleus of the atom and how, if it's unstable, the nucleus can kind of split off into different things. So we're going to be talking about radiation today. Alright, go ahead, and if you haven't already done so, put your phone away and complete the bell ringer in Canvas. You can go ahead and pause the video and take care of that, and then just come back whenever you're finished. And then go to a new tab and visit the website joinpd.com, and you can join this lesson using the code up here at the top right if we're doing this live or in our virtual class. So the code is JOKGCI. Go ahead and pause and do that. This is a mandatory step. You joining this lesson just allows me to monitor your progress, give you feedback whenever you answer questions, and just generally know kind of how you're progressing and how you're learning. All right, so do that. And then lastly, go ahead and get out some paper and pencil to write down notes, questions, and work example problems. The more you write things down, the more you remember. So I highly recommend for every single lesson you're taking notes, okay, because notes will help you learn. All right, next slide here. Okay, like I said, we're still in Module 1 and we're still talking about the atom, so that's not changed. And now we're on Section 4, nuclear radiation. So we're going to talk about different types of radiation, what the different particles that are emitted from the nucleus are made up of, and things like that. So we've got 3 different objectives to cover today. And the first one is to identify the symbols used for alpha, beta, and gamma radiation. So these are 3 types of radiation. And instead of writing the whole word, alpha, beta, and gamma, we use symbols to determine, or not determine, but to denote or identify what type of radiation we're talking about. So we're going to learn what those symbols are. The second objective is to identify examples of applications of different types of radiation. And then finally, we want to understand radioactivity in terms of alpha, beta, and gamma radiation. So just learning what each of these types of radiation means, what they're made up of, and what they can be used for. All right, review vocab. Remember, the nucleus is the extremely small, positively charged, very dense region that's in the center of the atom, and it contains the protons, which are positively charged. It also contains the neutrons, which are neutral. And it's surrounded by empty space through which the electrons move around. Okay. The key thing about the nucleus, if you're wondering why the neutrons are there, obviously the protons are there because that identifies the element, and the electrons are there to balance out the charge. But if you think about the inside of a nucleus, it's very, very small. If I pack in a whole bunch of protons, which are positively charged, in that very small area, like charges want to repel. So if I don't have neutrons in there to kind of space those protons apart, then they're going to want to repel each other, and the nucleus will just rip apart under the repulsive force. So that's what neutrons are for, if you were wondering. All right, here's our review vocab. So a lot here to talk about. We've got radioisotopes, penetrating power in terms of like what different types of radiation can go through, and what keeps you safe from different types of radiation. We've got radioactive decay, X-ray, radioactivity, and you can see the rest of them here. So we'll talk about different kind of particles, different types of radiation. We'll talk about nuclear equations as well. Okay, so all of these vocab words are on our plate today. All right, here's our main idea. So this is kind of a brief summary of the whole lesson. Under certain conditions, some nuclei can emit one of those 3 types of radiation, alpha, beta, or gamma, in order to become more stable. Okay. All right, so here I've got a little video. It's embedded in the slide. I'm not going to play it during this video, but I encourage you to pause this video and open this video in a new tab and watch it through before you go to the next slide of this video. So pause this video, open up the video on the slide in a new tab, watch, and then come back when you're finished. Okay? All right, so we're going to talk about the discovery of radiation. So radiation is fairly new to us in terms of like the timeline of scientific discovery. We haven't known about radiation or understood radiation for as long as we've understood other things. So it's still fairly new. Basically, what it boils down to is nuclear reactions can change the atom of one element into another element. And when I say nuclear reactions, I'm talking about reactions that happen within the nucleus of an atom. All right, so if I have something happening in the nucleus of an atom that changes the number of protons that I have, remember protons identify what element I'm talking about. So if I change the number of protons, I change the element. Okay, so nuclear reactions can do that. And whenever we talk about nuclear chemistry, then we're talking about the structure of nuclei. Nuclei is just the plural of nucleus. So we're talking about the structure of nuclei and then the changes that they undergo. That's what nuclear chemistry is going to look at. So we're looking at nucleus of an atom. And then there's this scientist by the name of Marie Curie. She and her husband Pierre were able to isolate the first radioactive materials. So these are the two people that kind of made the big discovery in terms of radiation and radioactivity. They were able to kind of isolate the first materials that were unstable and would just spontaneously emit radiation. Okay? And, her work actually ended up being what caused her death. She worked with radioactive materials, and as we know, radiation is harmful to our bodies, and she spent basically her whole adult life with these things. And eventually caused her to develop cancer, and it's what took her life. So really, she gave her life for science, which is crazy. Okay. All right, and of course, they noticed that some substances spontaneously emitted particles called radiation, and this process was called radioactivity. So if something is radioactive, that means that it emits particles from its nucleus, and it does that by radiation. All right. So here's a kind of a background of this guy named Henry Becquerel. So Henry Becquerel is another scientist that was a major contributor to radioactivity. And basically, you can read this and kind of see what his discovery was. It was kind of accidental. So he left a uranium rock in like a drawer with some photoelectric paper, photographic plate. And he left it there. After a while, he came back and opened the drawer, and he realized that the rock had imprinted an image of itself onto this photographic plate. And he reasoned that it had to be something to do with radiation. So he actually worked with Marie Curie and her husband, and they discovered radioactivity kind of together. So this is an interesting blurb about this guy, Henry Becquerel. He actually has a unit of measurement named after him. It's a becquerel, and it measures the radioactivity of a certain substance. So, fun fact. All right, I got another video here. This video is going to talk about Marie Curie's life. It's a biography. I'm not gonna play this video during this video. I encourage you to pause this one, open this video, open a new tab, watch it, and then come back whenever you're finished. Marie Curie is a very important figure in the scientific community with her work with radiation. All right. So we talked about nuclear reactions, how they occur inside the nucleus. How does that compare to like normal everyday chemical reactions? Because they are different. Okay, so chemical reactions, they involve electrons, which are outside of the nucleus of an atom. So whenever atoms transfer electrons from one element to another, they can gain electrons, lose electrons, they can even share electrons with one another. Those are chemical reactions, and those reactions happen outside of the nucleus. But whenever we talk about radiation and nuclear reactions, we're talking about nuclei, okay, right? The very dense region in the middle with the protons and neutrons splitting and giving off particles in the form of radiation. So we're not talking about electrons here. We're not talking about atoms reacting with other atoms. We're just talking about atoms that are unstable, that just kind of randomly give things off of their nucleus and emit things from their nucleus called radiation. So that's the difference. Chemical reactions happen outside the nucleus with electrons. Nuclear reactions happen within the nucleus with protons and neutrons. Okay? All right, so different types of radiation. So any isotope of an atom that has an unstable nucleus is called a radioisotope. We learned what an isotope was in yesterday's lesson, and that's basically just a version of an element that has a certain number of neutrons in it. So two isotopes, for example, would be the same type of element, like two carbon atoms, but they would have different numbers of neutrons. Okay? And if one of those isotopes is unstable, then we call it a radioisotope because it's radioactive. All right, and so unstable nuclei, they lose their energy and they get back down to a stable state. by emitting radiation in a spontaneous process. Spontaneous just means it's random, called radioactive decay. All right, so radioactive decay means it's going to emit particles out of its nucleus and then form more stable configurations or more stable non-radioactive elements. All right, so when something is very unstable, it's going to want to get rid of something so that it can become stable, and that's when it emits things from its nucleus to achieve that. All right, and there's three common types of radiation. They're alpha, beta, and gamma. We're going to talk about what each of these is. All right, so alpha radiation is made up of positively charged particles called alpha particles. And you might remember whenever we talked about Ernest Rutherford and the gold foil experiment, he was shooting alpha particles at a sheet of gold foil and observing how they passed through the gold foil, or in some cases were deflected back. So now we're going to learn what exactly those alpha particles were that he was shooting at the gold foil. Okay? So alpha particles, they have the same composition as the nucleus of a helium atom. So in other words, they've got 2 protons and 2 neutrons. So how do I know that? If I go to the periodic table and I find helium, it's up here at the top right. Okay? Here's helium. It's atomic number 2. So if it's a helium nucleus, that means it has 2 protons. And if you look at its mass number, it's 4.003. It's basically 4 flat. Okay? Pretty much every version of helium is going to have a mass number of 4. And if it has a mass number of 4, that means that it has 4 particles in its nucleus. If 2 of them are protons, that means the other 2 have to be neutrons, right? So that's where your alpha particle comes from. It's a helium nucleus with 2 protons and 2 neutrons. So the alpha particle will have an atomic number of 2, but a mass number of 4 because it'll have 4 total particles in the nucleus. Okay? So because of the protons, with no electrons to balance those charges, alpha particles have a positive charge. They have a 2 plus charge because there's 2 protons with no electrons to balance those out. All right, so the protons make an alpha particle have a plus 2 charge. And alpha radiation consists of a stream of particles. So it's not just going to be like a singular alpha particle. It's going to be a stream of particles being emitted and traveling in a certain direction. All right, and then whenever we talk about radiation, one thing that's of importance to us is whether or not that radiation can go through certain things and get into our bodies and impact the way that our cells function and impact the way that our body functions. So we need to know something about radiation's penetrating power. In other words, how well does it go through certain materials and potentially affect my body? Okay? So the ability of radiation to pass through matter is called its penetrating power. The more that it passes through things, the more dangerous it is to you. So the more penetrating power it has, the more likely it is to get in your body and harm you. So we need to know about those things. Okay? But lucky for us, alpha radiation is not very penetrating. In other words, it's very unlikely that alpha radiation will get into your body and cause you any real harm. Actually, a single sheet of paper is enough to stop an alpha particle. So if you have alpha radiation and you just kind of put a sheet of paper over your body so that the alpha radiation can't get through, then you're safe from the alpha radiation. All right, so here's a figure that shows a nuclear equation. Remember, nuclear just means it has to do with the nucleus of an atom. So we're looking at protons and neutrons here. Okay, and it shows the radioactive decay of this isotope of radium, radium-226, to radon-222. All right, so if I start with radium-226, if I find radium on the periodic table, it is number 88. It's right here. Okay, so number 88, which is why it has this 88 down there. All right, so it means it has 88 protons, and if I subtract the mass number minus the atomic number, then that tells me that it has 138 neutrons. Okay, and this is an unstable configuration. This is an unstable radioactive nucleus. So that means it's going to spontaneously emit an alpha particle here, and then it's going to turn into a different atom. So this is what this looks like. This element is unstable. It's going to emit something, and after it's done emitting, what I'm going to be left with is that alpha particle that it got rid of. It's a helium nucleus. And since I lost 2 protons, now I'm down to 86, and my new element is radon, right there. Okay, so I lost 2 protons, now I'm down to 86. My new element is radon, and I lost 4 total nuclear particles. So my mass number goes from 226 to 222. If you notice, both sides of the arrow, both sides of the equation are balanced. 226 is equal to 222 plus 4. Those should always balance, okay? Whatever you have on the right side should equal whatever it is on the left side. And then again, 88 is equal to 86 plus 2. So those should always balance. And again, this is my alpha particle. This is my helium nucleus. All right, so hopefully that makes sense. Okay, the next type of radiation is beta radiation. So beta radiation is radiation that has a negative charge, and it emits what we call beta particles. All right, so alpha radiation had a positive charge. Beta radiation has a negative charge. And each beta particle is just an electron. And an electron, remember, it has virtually 0 mass, and it has a 1- charge. Okay, so a beta particle is going to have 0 mass, whereas an alpha particle had a mass number of 4. Beta particles would have a mass number of 0. And then beta radiation is a stream of fast-moving particles, and it has greater penetrating power than alpha radiation. In other words, it's more likely to get into your body and cause harm, but a thin sheet of foil is enough to stop beta radiation. So if you've got some foil over your body, then you're protected from beta radiation. Okay? All right. The third type of radiation is gamma radiation. So gamma rays, they're pretty much around during alpha and beta radiation. So they are high energy radiation with no mass, and they're neutral. So no charge, no mass. Really, they're just kind of waves of energy that get emitted along with the particles that leave the nucleus. So they kind of accompany the other two. And there it is. So gamma rays almost always accompany alpha and beta radiation. You hardly ever have gamma radiation by itself. It's always going to happen because you have alpha or beta radiation going along with it. Okay, so these alpha and beta are the particles that get emitted. Gamma rays are the energy, the waves, the energy waves that get emitted. Okay, and they account again for most of the energy that's lost during radioactive decay. So gamma rays have a lot of energy associated with them. And they are highly penetrating. Gamma rays are what you need to be careful about whenever you're dealing with radiation, because they have no charge, so they're not deflected by anything, and they have no mass. So, it's very difficult to stop gamma radiation. X-rays are a form of gamma radiation, and X-rays are emitted from certain materials that are in an excited state. Excited just means they have a whole lot of energy that they want to release, and they'll release that in the form of gamma radiation. And that's what, whenever you go to the doctor because you broke a bone, and they take your X-ray, that's what is being put into your body, is these gamma rays. All right, so now you know. Just be very careful about how many X-rays you have to get. Make sure you take care of your body so that you don't have to expose yourself to a lot of radiation. Okay. All right, this table summarizes the three types of radiation. So we have alpha, beta, and gamma. Remember I talked about there were symbols for each of these? So you can write alpha radiation one of two ways. You can write it as the helium nucleus notation right there. So, it's a helium atom with a mass number of 4 and an atomic number of 2. You can write it like that, or you can write it like the Greek letter alpha. Starting at the top right, you just kind of loop, and it almost looks like an A, but it's Greek. So 2 ways that you can represent alpha radiation. If you see any of these symbols, then know that it's alpha radiation. It's a helium nucleus. It has a mass of 4, because 2 protons, 2 neutrons. And it has a charge of +2, because those 2 protons don't have any electrons to cancel them out. Right? Beta has a symbol of E- for electron, or a Greek letter beta, which kind of looks like a funny B for beta. Okay? Mass, it's virtually 0. Again, it's an electron. It's 1,840 times lighter than a proton. All right? But it's practically 0. And then it has a charge of 1- because it's an electron. Gamma looks like this. It's another Greek letter, And you make it by kind of making like an upside down ribbon. Start at the top and just kind of make a loop down there and come back up. All right, it has a mass of 0, no charge, no mass, no nothing. It's just high energy waves that get emitted during one of these two types. Okay? All right, so here's an example of just showing the different types of charge that radiation has. So if I have radiation being emitted from this radioactive source, and I streamline that so that all the radiation travels in a straight line through this hole, if I have a positive plate here and a negative plate down here, opposite charges attract. So whatever's negatively charged is going to be attracted to this positively charged plate. So you can see that beta particle is going to curve upwards because it's attracted towards that positive plate. Okay, and it'll end up here at the top. Whereas a negative plate attracts the positive alpha particles, and you can see it kind of curves downwards towards the bottom. But gamma rays, look, they have no charge. They are not deflected by anything. They just continue onto their path. They are extremely, extremely focused. Nothing can get them off of their path. All right. So that is it for this lesson. I just wanted to show the different types of radiation and talk about those and distinguish between those three. So go ahead and give me your dot. Tell me how you're feeling. And while you're doing that, I want to show you a couple of FET simulations that I found. So if you Google FET beta decay, this will show you beta radiation. Right here, I've got a hydrogen nucleus with 1 proton and 2 neutrons. If I hit the play button down there, you'll see it shoots an electron out of it, and look, it turns into a helium atom. So it turns into a helium atom because one of those neutrons emits an electron and basically converts that neutron into a proton. So anytime you have beta radiation, you gain a proton. You lose an electron, but you gain a proton. It's kind of weird to think about, but I would play around with that simulation to get comfortable with that. And then this one, if you Google PHET, P-H-E-T, alpha decay, you can see this is a polonium atom. Polonium-211 is a radioactive isotope. If I hit play, then give it a second, and you'll be able to see the alpha particle get emitted. See, I lost a mass of 4, and now my element is lead, Pb, because I lost 2 protons. All right, so you can play around with these simulations. I really like them because they kind of illustrate what this radiation looks like instead of just me telling you about it. So I recommend that you go and play with those simulations too if you can. All right, but go ahead and give me your dot. Let me know how you're feeling. That way I can, get a feel for where you're at. All right, we're finished with the lesson. Thank you guys for sticking around. Let's go ahead and get these multiple choice questions. So why do radioisotopes emit radiation? So think about this. Pause the video, answer the question. Whenever you're finished, unpause, and I will reveal the answer right now. Okay, so if you said radioisotopes emit radiation because they want to become more stable, then you're correct. Radioisotopes, they are radioactive because their nucleus, the way it's structured, is very unstable, and it wants to get rid of something so that it can become more stable. All right, stability is like the main reason why things happen in chemistry. If things are unstable, they're going to do something until they become stable. So these nuclei are unstable. They're going to get rid of things to achieve more stability. All right. X-rays are most similar to what type of nuclear emissions? Think about that. We talked about which type of radiation this corresponds to. So pause the video, give me your answer, come back when you're done. I'm going to reveal the correct answer right now. And if you said gamma rays, very good. Remember, gamma rays are the most dangerous type of radiation because hardly anything can stop them. They can get into your body. They can mess with the way your cells function and your body functions. And so it's good to limit the amount of gamma radiation, limit the amount of X-rays that you're exposed to so that you can stay healthy. All right. So if you said gamma rays, then great job. Now that's it for this lesson. So if you have any questions about today's lesson, then you can ask them here. Just go into the response thing on the Join PD, type a question, and I can go in there and give you feedback. Go ahead and complete the exit ticket for today. And then on Canvas, there is an assignment due for this section. And this is section 1.4. So if you go to Canvas under Module 1, the assignment will be 1.4.1. I think it's the isotope research assignment, so that'll be due tomorrow. All right. So that's it for this lesson. If you have any questions, feel free to reach out to me in whatever communication platform you use to connect with me, and I will get back to you as soon as possible. Hope you learned something today, and I will see you later.